Yeah, thank you for having me here. I'm Herbert, as I was just introduced. I'm a scientist developer at Fantom. I'm working there since about a year, and Fantom itself is an Ethereum-compatible blockchain that is aiming for low time to finality, low gas costs, and our new goal is also strong scalability, that we get to larger amounts of transactions per day. And the goal that we have set internally for us is the 100 million transactions. As we have talked through the last days already, there are technical challenges. I'm a scientist developer. I focus on the technical part. So forgive me for that. There are 5 big problems that have been named earlier this year as the critical problems for blockchain technology. Forbes has listed those. It's scalability, energy consumption, security, complexity, and interoperability. Some of those may already have been covered, like energy consumption with the transition to proof of stake. The one that we are aiming at the moment is scalability. And we have heard also several talks today already about this topic. So why is it technically, what's it in technically, what are the numbers? What are we facing here? At the moment, chains like Ethereum, or also our own chain, can do about 2 million transactions per day. That's kind of an estimate. That's what we saw at the peak of the market. The actual reality today is more around 1 million. But this means it can do 25 transactions per second, approximately that. But for reference, if you would implement something like a card paying system only in the US, you would need 100 million transactions a day. And worldwide, it would be orders of magnitudes more. And this is in the scope of 1,200 transactions. So we need a 50 times improvement in performance that we could get through if we ever want to handle something like a card paying system on our chains. What's the technical problem, though? So to get something into a block, 2 steps have to be fulfilled. One, nodes in a network have to somehow agree what should be in the block, which transactions should be there, in which order they should be. And then once this has been packaged together, nodes need to be capable of performing those transactions, executing them on the state, get the updated state, and put this new state hash into a new block. It turns out, so the first one is mostly limited by the protocol complexity, which is used for obtaining the consensus and the network speed, while the second one is a local processing problem. So all the transactions are already on the node. It's just depending on how fast can those transactions in the EVM actually be executed and how fast can the state accesses be performed. And it turns out, in Fantom at least, this is the bottleneck. Most of the time, why we can't just tile up and put hundreds and thousands of transactions in this block is that we just don't have enough time to process them in every block, which in Fantom is every second or 0.7 seconds. There are solutions for this. We have seen them already presented on the stage today. Some go for layer 2 approaches, where you roll up larger sets of transactions, put them into one transaction on the mainnet. Others are proposing sharding, which is basically splitting the network into smaller subsections and have each subsection work a smaller set of contracts. But both of them, they add complexity again to the system. And they weaken the security. We have heard of this blockchain trilemma. What we think, some resource that is not fully explored, though, is software efficiency. Can we do the same things with the same architecture without any changes, just more efficiently? And that's what we are currently working on. We try to make faster EVM and faster state. So how do we do that? When we started working on this, we adopted an evidence-based development cycle. So basically, every idea, everything we would like to change, we put into a prototype. We pass this prototype through an extensive test, so conformance tests, that we make sure that these changes are actually viable in reality and we don't break anything, any backward compatibilities. And if this is passed, we put it on a test stand. Basically, this means we run all the entire block history through those changes, see whether what is the effect of this change, of this new idea, of this design change that we want to experiment with in an actual environment. We're running all of those transactions. It's about 50 million blocks by now, 60 millions. We run the entire history through it. We collect data, we collect CPU times, memory accesses, profiling data, and we study it. And we learn, we see whether the idea that we originally had actually materialized, and we find new ideas for the next cycle. Traditionally, this cycle, when we started a year ago, it took 1 to 2 months. And the longest phase is the evaluation phase, because rerunning the entire history of your blockchain takes weeks. with the current technology. But with what we have built here with the cycle, we spent a large number of resources also within our team to improve this cycle time so that these days we can do it within a week. Essentially, we run the evaluation over a weekend, we study the results on Monday, we have an idea on Tuesday, we implemented Thursday, Friday test, Wednesday, Thursday, we test them on Friday, iron out all kind of problems, and have another weekend run for the evaluation. Internally, we have grouped our tasks in several projects. We name them using Opera names because our client is the Opera client. The test and evaluation infrastructure is the project AIDA. This project enables us to run all the 50 million blocks history that we have in Fantom within 24 hours and get all the metric information, all the CPU information that we want to know from it, all in one go. And it's the foundation for our evidence-based development loop. Basically, we have standardized this. We have one team just building and evolving this tool, and we have multiple teams then working on an EVM or a database extension, maybe even multiple versions of this, and all are evaluated against the same benchmark so that we can compare the results of various sub-teams and people having different ideas and different opinions, basically on facts. We run it, we test it, we get the results. And this is steering our development. One of the earlier results we saw is that when it comes down to the block processing, the actual execution time is vastly dominated by the state DB. As you see here, around 80% of the execution time is actually spent in the DB and not in the EVM. So our original goal was to find a faster storage solution. Because if we can improve this by a factor of 10, we can cut down we have the highest impact for what we invest. This project was titled Project Carmen, another Opera. And the idea is that we basically go in without any biases. We want to try all kinds of ideas. What is it if we change the data format? What if we change the programming language? What if we change the hash algorithm? What impact does it have on the performance and on the usability of the system in all? And Carmen's task was to establish a framework to get those prototypes quickly developed, to get it correctly through the evaluation process so that we can reuse components, basically like a toolbox, and then to explore and understand the design space for storage solutions in an EVM-based blockchain. And with this, we learned, we started to understand what is important, what are the critical components, what can be pruned, what can be removed, what is the expensive part. Some key insights is, and some of you might not be surprised with this, one of the performance bottlenecks is the key value database. So what you might know as LevelDB or Pebbles or similar systems, this system, which is basically the foundation of many implementations, is what takes most of the time. And if you make this more efficient by tuning parameters or replacing it by alternatives or even more direct accesses to the disks, you can gain a lot of performance. But to do this, you need disk-friendly access patterns. So random access to the disk, even if it's an SSD, is super slow. It will ruin all your performance by an order of magnitude. If you can get it done so that the accesses are more efficient in groups, also maybe by introducing caches to improve this gives you a huge boost. And we also learned that the use case of a validator node that just needs a live DB and the use case of an archive node are very different, and you can gain performance by separating those two and having basically two versions of the DB. One for the live serving that is destructive, so when new data is coming in, you override it, and the other one that keeps all the history, but it doesn't have to be as fast for processing it because it has the time while the consensus is running to catch up. Once we did this, we had a database that is fast enough that now the EVM is more in the spotlight for being the performance bottleneck. And we repeated the same process, right? We had a lot of ideas on how to do this. We still have a lot of ideas for doing that. Everything from using different languages to improving analysis, doing JIT compilation, using WebAssembly. And we, again, built the platform. We try to understand what does it take to build a real fast EVM and learn from this. The key learnings there is that the language indeed matters. Whether you do it in Go or in C++ or Rust, it makes a big difference. But also details. If you use the same language and you do the stack that you use within your EVM, if you do it slightly different, it has a huge impact on the performance that you can gain in the end. Another thing is that while the execution of the EVM is usually what you might think is the costly part, it turns out that for standard contracts, the jump test analysis, which is one of the components required for correct execution, is critical and sometimes dominating the execution time by a factor of 3. That could be quite substantial, and getting these costs down is essential for improving performance. And last, something, I'm from a compiler background, VM background from my research, the characteristic of an EVM is very different. Standard optimizations you would do in an EVM, like hotspot optimizations, don't work in an EVM because you don't have loops, you don't have a lot of repetition, everything is priced. So optimizations you might see in off-the-shelf VM implementations might just not work for you, or it would have to be reconsidered whether this is actually of any sense in your environment. And we saw that some of those tricks we just don't even have to attempt, and there are other tricks that you can attempt that in a standard EVM might not pay off at all. We took both of those systems, Carmen and Tosca, we developed various prototypes, and if we take both of those together, we run the 50 million blocks for evaluation. The result, every week we get one of those graphs. I'm sorry, this is only until 40 million. It's I took from an older presentation. We see the block range from 0 to 40 million. The blue line is the performance that we get with the standard GEF client using the GEF EVM and the GEF StateDB. And its performance is all around 600 transactions per second, only when you run it. So it's just the block processing, it's not involving the network. In comparison to this, with our Tosca and with our Carmen implementation, we can reach almost an order of magnitude higher throughput. It's around, if we go for this is the entire history, we get stable improvement. Some peaks are where there is special load in the network. If you sum it all up, the execution time is 8 times faster. We get 8 times higher throughput with those modified implementations that are still in Go versus the standard GEF client. But another exciting side effect is that we not only improve the performance, we could significantly reduce the storage requirement as a side effect. Every time when you reduce the memory footprint of something, you get it faster because you have to transfer less information from the disk to the main memory and back, and also moving it around in the main memory is expensive. By redesigning the database, we managed to reduce it by 89%. What used to be 1.2 gigabyte in GEF, in its key value-based storage, in our system is around 30 gigabyte at the moment. We are currently having now these systems. They are in a prototype state, but we are working on now putting it in the testnet. We have new test environments where not only the block processing is covered, but also the node startup, the synchronization, failing nodes, error cases, and we try to harden the code. And we aim to launch the Carmen results by the end of the year, or have it launch ready on our mainnet, and as well Tosca. Continue the development. Tosca is a bit easier to launch. You will not need a hard fork for that. It's a complete simple replacement. And also then there are future long-term improvements that we would like to apply. We don't do yet any parallel thing. Everything that you see, the transactions are still running sequentially. We want to go parallel with those. And we think about providing an alternative decoupled client from the Go standard client, go into the C++ environment, and use all the performance potential that we have found with our prototyping there. So that's all. Thanks for staying around, even for the last talks. I'm also sure the following presenters will be happy about that. If you have any questions, please feel free to contact me here or outside. And have a nice evening and enjoy the rest of the conference.